In this video, we're going to learn how to work with the properties of logarithms. Now, I wrote down several statements over here that I'm going to go through before I start. The first property is log base anything of 1 should always equal 0. This being is that if this log is equal to 0, that's the exponent, so anything raised to the 0 power should be 1. Same thing over here is anything raised to the first power should be itself, so log base b of b is always equal to 1. Now, since exponentials and logs are inverses, you'll often see them arranged in a way where they can cancel each other out and you're left with just the variable. But the way that works is that if I have b raised to the power of log base b of m, if that log is the power you raise b to get m, if I raise b to that power, I should just get m. Same thing over here, log base b of b to the r. This log is equal to the power you raise b to get b to the r. Well, that power should be r. Now, the next three are very popular logarithmic properties. The first one's the product property. Whenever you would multiply two factors on the inside of a logarithm, they can be split up to be log base m plus log base b of n. Now, where that property comes from is multiplying two exponential expressions. You'll add their exponents, and since logs represent the exponents, it makes sense that if I'm multiplying within a log, I can write it as log base m times plus log base n, because if I have m times n, like these two expressions, their powers should add together. Same thing with division. Normally when I divide two exponential functions, I subtract their powers. So it makes sense that the two logs should be subtracted if I were to separate those into two logs. And if I have a power within an exponential function, that can actually just multiply to the logarithm. And that same knowledge comes from whenever I raise a number to a power, I can multiply their powers together, since the log would represent an exponent, just like r would be in that expression. And the last two are a way of a play on these two expressions up here, to where if you have e to the x natural log of b, since the natural log in e could cancel out, I'll be left with just x, and then that b becomes the base. Because of this little expression here with the m, that would go down to the base, but the x would stay in the exponent. Same thing with the common log. Now let's put these to practice. So if I had 2 to the log base 2 of pi, that's using this property up here. So log base 2 of pi is the power you raise 2 to get pi. So that makes sense for this expression just to equal pi. Almost as if those two just canceled each other out. Same thing down here, log base 0.2 of 0.2 to the negative square root of 2. The power you would raise 0.22 to get 0.2 to the negative square root of 2 would be the square root of 2. So those are like your cancel out properties, these two right here. Now let's say I have log base 8 of 16 minus log base 8 of 2. Well, I could combine both of these logarithms into one using this property. Since I'm subtracting, I can write this as log base 8 of m divided by n. So 16 divided by 2, which gives me log base 8 of 8. And I just talked about earlier, if the bases match, the power you raise 8 to get 8 is 1. So that just simplifies to 1. Now, if I have e to the log base e squared of 16, what I can do is rewrite this, because right now e doesn't match the e squared. But what I can do is write e to the second times 1/2. 2 times 1/2, which is 1, times the log of e squared, base e squared of 16. And that 1/2, I could put e to the second e squared times the log of e squared 16, all to the 1/2 power. So now I have e squared matches that e squared, which means I can use that similar property I saw before, leaving me with just 16 to the 1/2 power. Now the 1/2 power is the square root, so the square root of 16 is 4. And lastly, I have log base 3 of 8 times log base 8 of 9. Now, since they're being multiplied, one of those two things being multiplied, or in this case could just be a log, could become the exponent of the other log. So this factor here could become the exponent of 8, giving me log base 3 of 8 to the log base 8 of 9. So it just became the exponent of the inside number. Whenever you multiply two logs, one of them can become the exponent of the other using this property right here. Now 8 to the log base 8 of 9, we just saw that used before, like multiple times. Those will cancel, leave me with just 9. Log base 3 of 9, which to get log base 3 of 9, I have to ask myself, what power do I raise 3 to get 9? Well, that's the second power. So log base 3 of 9 is 2. Now for these next examples, we're going to suppose that natural log of 2 is a, and natural log of 3 is b. And then we're going to rewrite these expressions to be in terms of a and b. So if I'm looking at natural log of 6, 6 is also known as 2 times 3. So I'm going to write natural log of 2 times 3. And using my product property, I can separate that into two separate logs, natural log of 2 plus natural log of 3. And since I know that natural log of 2 is a and natural log of 3 is b, that can just become a plus b. So these are little exercises in using the properties to rewrite expressions. I have natural log of 2 divided by 3, so I could separate those with subtraction using that quotient property. So it could be natural log of 2 minus natural log of 3, making this natural log of 2 is a minus natural log of 3, which is b, a minus b. Now natural log of 0.5, I don't see a 2 or a 3 in there, but I can write this as the natural log of 1/2, which now I can see that 2 take place, and I can use that same property I just used before to get natural log of 1 minus natural log of 2. Now natural log of 2 is a, like we just discussed, but natural log of 1, log base anything of 1 should always equal 0. So natural log of 1 is 0, giving my final answer just to be negative a. Now natural log of 8, there's no 2 times 3 or 3 divided by 2 that will give me 8, but 8 is 2 to the third power. So I can rewrite this as natural log of 2 to the third power, then use this property down here with the exponent and move it out in front of the log to give me 3 natural log of 2, which natural log of 2 is a, so I just get 3a for my expression. Something similar can happen here. I have natural log of the 5th root of 6, which I talked about these radicals before, but the 5th root can be written as 1/5 in comparison. So I have natural log of 6 to the 1/5 power, which I can move to the front just like I did earlier. So I get 1/5 of the natural log of 6. The natural log of 6 can be written as the natural log of 2 times 3, which can be separated with addition using that product property. So I get 1/5 times the natural log of 2 plus the natural log of 3, which leads me to get 1/2 natural log of 2 plus 1/2 natural log of 3, the expression 1/2 a plus 1/2 b. And then something very similar can happen with this last one. I can get 1/4 natural log of 2/3, since the 4th root could be the 1/4 power. That can be separated with subtraction because it's division, so that can separate with subtraction. So natural log of 2 minus natural log of 3, which is a minus b. So I get 1/4 of a minus b. Distributing the 1/4, I get 1/4 a minus 1/4 b as my expression. And that is how you work with the properties of logarithms.